Hello and welcome to the Open Systems Media eCast titled Managing Size, Weight, and Power, also known as SWaP, in Military Embedded Systems. My name is John McHale, Group Editorial Director with Military Embedded Systems magazine and moderator for today's event. Our speakers today are Mike Southworth, Product Marketing Manager for Curtiss-Wright Defense Solutions, Justin Moll, Director of Marketing for VetaTech, and Wayne McGee, VP with Creative Electronic Systems. Now for some housekeeping announcements. This eCast will consume about 35 to 40 minutes, leaving the remaining time for the question and answer session. And before I get going, I want to point out three important buttons on your screen. First, please take note of the Enlarge Slides button. By clicking on this button, you will be able to view the slides in full screen mode. The next important button is the Forward to a Friend button, which enables you to email a friend to register for this event. The third button on your console window enables you to enter questions in real time. We will do our best to address these questions during the closing Q&A session. If you have a question intended for a specific speaker, please note so at the beginning of your question. Otherwise, I will hand out the questions equally to all of our speakers. If you have a question pertaining to the eCast operation itself, one of our technicians will respond back to you during the eCast. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the eCast with more information. This eCast will be archived online today and be available for 1 year. There will also be an MP3 version of the event. And now I'm pleased to turn over to our first speaker, Mike Southworth of Curtiss-Wright Defense Solutions. Mike?
Thank you, John. Good afternoon or good morning to those on the call. We speak of managing SWaP or SWaP optimization today, but this is ultimately not done in a vacuum without considering a lot of priorities and trade-offs that military embedded systems electronics have to go through well beyond SWaP. So, for example, we should also consider the cost, the performance requirements, the supported features or capabilities of the device, the reliability under the deployed extreme environments, or the thermal management or cooling techniques that will be required, your schedule, your lead time, use of COTS versus custom, the length of life cycle you need to support, your obsolescence mitigation plan, and plans for upgrading or scalability. At Curtiss-Wright, we aim to optimize SWaP in that context of all these trade-offs with our customers and provide the best overall solution for customers. And thanks to recent advancements in technology, we are achieving some impressive new things. SWaP reduction for us is a key focus, especially for our next generation products. We have a long legacy of experience working with military system integrators, deploying SWaP optimized products on hundreds of land, air, sea platforms. We carry on that legacy of the Wright brothers who invented power flight more than 100 years ago. Today, we're the largest supplier of embedded COTS modules and subsystems for the defense and aerospace industry. We have a very large portfolio of COTS products that span mission processors to data storage devices to Ethernet networking devices and hundreds of board-level building blocks. A noteworthy example of a recent success in SWaP reduction achieved here at Curtiss-Wright is with our Parvis Duranet Gigabit Ethernet switch products. The latest model, called the 2011, provides 8 ports of fully managed Gigabit Ethernet switching in an ultra-miniature form factor that is just 10 cubic inches in size. Now, this represents a 90% size reduction from the next smallest Gigabit Ethernet switch subsystem we've offered. Applications, particularly unmanned air systems, are driving demand for such small network connectivity devices. And component miniaturization is helping us achieve this SWaP optimization. So here's a case in point. Curtiss-Wright developed a small form factor 20-port Gigabit Ethernet switch module recently in the PCIe 104 form factor. And this represents the smallest, highest port count rugged COTS Ethernet switch card available today on the market. This was achieved in large part due to the tight integration of functionality available today in system-on-chip packages. And in this case, it provided a switch that integrated 20-plus ports of switching plus a MIPS processor for management, 12 copper physical transceivers, DDR memory controller, and a 1588 precision timing protocol controller all in one package. And at the system level, also the switch core and the PHYs feature various power management technologies that have cut power consumption in half compared to traditional Gigabit Ethernet switching. This particular PCIe 104 board was a key building block for us in a small form factor system, the Duranet 2010, which ultimately gave us a 60% reduction in SWaP from the previous Gigabit Ethernet switch model. But ultimately, this is an evolution, and it continues. That same technology developed for the 20-port system has now been reused and adapted to create an even smaller 8-port line replaceable unit that is less than 10% of the size of the 20-port unit and less than 25% of the weight. This small LRU, which fits literally in the palm of your hand, integrates several smaller PCBA assemblies to accommodate the switch, the Ethernet magnetics, and the power supply. It also has miniature low performance connectors that are roughly half the weight, half the size of a traditional larger DTL 38999 connector. Now this level of miniaturization is enabling SWaP-sensitive platforms like aircraft and ground vehicles to integrate LAN connectivity and more payload electronics than ever before to satisfy mission requirements. Similar advancements are being made for processor, CPU, silicon devices thanks to advanced die manufacturing processes. These CPU devices are now more energy efficient than ever and provide more performance per watt. Their clock speeds tend to not be increasing much with each generation, but the number of cores available is, and the power consumption is dropping. Some have also built-in GPU engines, which are very impressive. In fact, some of these graphics processor engines are enabling systems to eliminate a separate GPU card entirely. Some examples of Intel processor architectures that we're working with that fit into this would include the quad-core mobile-class Core i7 processor, where the diameter of the die has shrunk now down to 14 nanometer with the 5th generation processor coming out. And performance improvements are quite notable. We anticipate a 60% bump just in the graphics capabilities from this 5th generation versus the last. And there are other x86 system-on-chip products that fit into other classes of computing. For example, the Xeon D processor now is a system-on-chip that is capable of delivering up to 16 cores with a total TDP power of 45 watts. Or, of course, the Intel Atom processor, which supports up to 4 cores, less than 10 watts TDP. Now, these low-power, highly efficient system-on-chips and system-on-modules are now available for not only x86 processors, but also ARM core CPU architectures. These are low-power processors, so we're talking 5 to 10 watts TDP max, which makes thermal management a lot less complex because now systems can have less surface area required for cooling. Curtiss-Wright will be introducing several miniature dual-core mission computers soon with options for both x86 and ARM CPUs, coupled with I/O expansion capabilities for PCI Express mini cards. Some of these systems are expected to yield a 75% reduction in size from the high-power Core i7-based systems, yet still deliver a moderate level of performance with up to 4 cores of processing at less than 10 watts, which is impressive. Now, there's a wide spectrum of standards-based small form factor modules available from VITA, PICMG, PC104 Consortium, and other standards bodies when it comes to processors and I/O cards. Some of these modules are shown here in this slide. You can see a comparison of their relative physical size. For you, VPX architectures, for example, are ideal for combining multiple SBCs, even including a mix of x86, power, ARM architectures all in the same system, using a high-speed backplane and XMC I/O card expansion. Whereas other small form factors like ComExpress or PCIe 104 or other system-on-module standards like SMARC, for example, are generally used in a single processor system, but commonly with PCI Express mini card expansion. Now, this wide variety of small form factor standards enables Curtiss-Wright and our customers to optimize SWaP and the performance level to meet varying different customer requirements. Now, interestingly, we've been able to combine many of these standards into a single hybrid type of architecture that has yielded us a SWaP reduction of 25% in our latest Core i7-based systems. So rather than using a PCIe 104 SBC like in the previous generation product, which required more complex thermal management devices to be used and multiple interface boards that complicated the design, the new model, which is referred to as the DuraCore 8041, integrates a COM Express processor as a mezzanine card on a carrier board, which features slots for I/O expansion through mini PCI Express, MSATA, and PCIe 104 I/O cards to be added. And the result is not only a 25% SWaP reduction, but we now have a very flexible, smaller, lighter, and a more powerful system that now has double the RAM capacity of the previous generation, built-in I/O expansion, and a more efficient thermal management design. And in fact, this design is able to perform at 100% stress test of the CPU and the GPU at 71 degrees C ambient operating temperature without throttling below the rated clock speed. And just to further illustrate the point, this is an exploded view of this type of architecture showing multiple small form factor modules being used with a carrier and a processor mezzanine. And this approach also enables us to have a drop-in migration path for the next generation Core i7 processor product when it's released by Intel. Now, we've talked about modular board architecture, but there's also modular subsystem level architecture, and that's enabled us to reduce SWaP aspects. In this case, we're talking about consolidating what were formerly standalone LRUs, so a mission computer or a network router or an Ethernet switch, now into a multifunction device. High-performance Core i7-based processors can now be paired with, say, a Cisco router or a Gigabit Ethernet switch in an all-in-one scalable chassis. In addition, we're introducing low-power ARM-based vehicle electronics computers in the Digital Beachhead family that provide quad-core Freescale ARM processors, together with 16 ports of Gigabit managed Ethernet switching, along with support for integrated military GPS receivers. This next-generation all-in-one solution is really 50% smaller than the previous, and yet it's still capable of supporting Victory Shared Services processing and infrastructure switch requirements needed by the U.S. Army. In addition, these systems, again, still leverage the modularity from add-on I/O module slots from many PCI Express and other form factors. One final SWaP reduction approach I'll mention today is that we can consolidate networking and processing functions in a single device by using software. Software-based networking and hypervisor virtualization applications enable us to now deliver Layer 3 secure mobile routing and VPN encrypted security functionality via software on a general-purpose x86 processor platform. So this is a bolt-on software approach that provides the same feature sets that you would find in the physical hardware-based device, but now it's in a format that can be loaded onto a computer that does not add any physical weight or size to the LRU. It just uses a portion of the processing capabilities. So to sum up my points that I shared with you today, SWaP reduction is being realized at Curtiss-Wright through miniaturization of components, through the use of modular open architecture standards, by leveraging highly integrated and low-power ARM and x86 processors, and also by consolidating LRU functions into a multifunction appliance through either a hardware consolidation or through software bolt-on options. So thank you for your time today. I'll turn the time back to John.
Thanks, Mike. Good presentation. And before I turn over to our second speaker, I just want to encourage the audience to keep your questions coming in. Once our third speaker is finished with his presentation, we will start our Q&A. And now for our second speaker, Justin Moll of VetaTech. Justin?
Okay, thank you, John. So as we talk about SWaP-C, we know there's a continuing drive for higher performance and less space. And part of this is really ideal to try to leverage open standard architectures so that you can have the modularity, scalability, reuse of hardware, multi-vendors, and so on, all those advantages we like. So today, I'll be talking more about the different type of architectures and where they fit and some of their SWaP levels and where they fit best. And this includes legacy architectures such as VME and compact PCI, VPX, MicroTCA and corresponding AMCs, and small form factor solutions. And the core markets we're talking about are a lot of the radar applications, sonar, electronic warfare and signals intelligence, also communication networks, and different types of command and control situational awareness applications, and any applications that require high performance signal processing. So as we look through the signal processing chain, we'll be talking about from the front of the chain, from the initial input all the way through the actual output on the other end. So from data acquisitions and signal processing with A to D converters and high performance FPGAs, to the data processing and information processing with the different types of high-end processors and GPUs, and as well as data storage, which can happen at various points throughout the signal processing chain. So where do the different open architectures fit? If you have more space available and you need the high performance, you're able to use the larger architectures such as 8U Advanced TCA and 6U VPX. And here we're talking about the board size, not the size of the chassis. As the performance requirements go down, you could still use some legacy VME and compact PCI. But as your size allowance starts to decrease, you need to start to look at more of the 3U sizes in EuroCard and MicroTCA and AMCs. As you continue to go down the size spectrum, you're limited more to MicroTCA sizes and some of the new open standard VITA 70 series architectures for small form factors. So we set up MicroTCA as the solution for medium to high performance mil-aero systems in the medium size and above small form factor on up. It's a very well established architecture with broad deployment in both commercial and mil-aero applications. The AMCs have been in advanced TCA systems for over 10 years. It's an open standard architecture with very wide multi-vendor ecosystem across all types of functionality, including FPGAs, A to D, D to A to converters, storage, processors, graphics, switches, and so on. So looking at the size and performance comparison with the legacy architectures and VPX and MicroTCA, aside from the size differences, you can see that MicroTCA offers the system and health management, electronic keying, where the system can identify the types of boards and fabrics utilized in the system, advanced clocking features, high availability if that's needed in the application, up to 7 nines uptime, and high interoperability. So comparing with EuroCard, as a rule of thumb, we say that MicroTCA is roughly about half the size and weight of 3U EuroCard. And for the cost, it's roughly, for VPX, about half the cost. And if you look on the right side, you could see some of the size differences there. In regards to the cost, part of the reason that's possible is because MicroTCA is truly a COTS architecture where it's used in various industries such as mil-aero, physics, communications, and many others, versus VPX, which is a great architecture but tends to be more focused towards military applications. Since MicroTCA is across various industries, there's a lot of economies of scale in using those same chipsets and components across multiple platforms, helping to drive down the cost. MicroTCA is also a truly interoperable architecture with consistent pin assignments for every slot. VPX is, as far as the interoperability, you tend to require custom backplanes, and the different modules that you could use with others tends to require reviewing the different profiles and their compatibility. So what about small form factor solutions? Well, there are a lot of great solutions out there that fit various performance levels. One of the issues that most of these are proprietary solutions that have more of a single purpose and for customized applications. And many of them, as far as the performance, don't address your higher processing performance and I/O levels that are required in many of these challenging applications. As far as some of the open standard efforts, we'll learn more about VNX and some other in the next presentation, but there isn't a consensus yet on these architectures. So the effect as a ecosystem for small form factor, there really isn't the effect that you have is there's little reuse of the technology, you have a smaller ecosystem, and this causes a bit more risk, and there's little to no scalability, and upgrades can become an issue. So again, looking at the performance level, the small form factor do a great job up to a certain level of performance, but for the requirements where you need more of the processing power and I/O network interface, you really need to look at architectures such as MicroTCA. There's also, as far as the ecosystem diversity, the different types of modules you could choose, whether storage or graphics, and the different ones that we've talked about. MicroTCA has the richest ecosystem. So to give an example, this is a 1U rugged chassis designed to meet MIL 810 and 901D for shock and vibration, and versus a typical Eurocard application, this may be a 3U or possibly even a 5U chassis, so a lot more performance density, and you could have up to 6 AMC slots in a rugged version, and actually in the commercial version, by employing a deeper chassis and having some of the slots plugged from the rear, you could actually have 12 slots in a 1U chassis. And there are other features in this application where there is integrated GPS Sync-E IEEE 1588 for precision timing and time stamping, as well as the inherent system management of the system. So this slide shows that standard AMCs can be ruggedized with clamshells put around them, and the chassis shown in the middle can be started in your initial prototyping and deployment. You could go to a ruggedized conduction-cooled version per MicroTCA.3. So in your tightest requirements, when you really start to get down to the smaller SWaP size, an option is to use standard AMCs within specific designed conduction-cooled or other types of small form factor chassis. Typically these are 2 to 3 slots, typically conduction cooled, and tailored to the size and thermal requirements of the application. And the advantage here is you're leveraging open standard architectures, that hardware, the firmware, and so on, in a small form factor size. A couple of application examples is you could have 2 of these AMCs for a signal processing solution with dual Vertex 7 FPGAs that have host power PCs on them, so each act as an independent host, with a FMC carrier holding very high gigasample per second digitizers. Alternatively, you could have more of a storage platform where you could choose different types of AMCs from SSDs, line rate speeds, integrated RAID controllers, or even AMC modules with JBOD where you could have up to 8 terabytes mSATA all in one little AMC. A couple of application examples. The 1U chassis we saw earlier is being used in deployed radar signal processing application with multiple FPGAs, again with the FMC carriers on there for high performance, high gigasample per second A to D and D to A converters, high performance Haswell processors, and integrated RAID storage, all in a 1U solution. Another concept is to add multiple of the JBOD carriers in the chassis for up to 40 terabytes of RAID storage, again, all in the 1U size. Another interesting application was a 5U electronic warfare platform that used a 5U 12-slot MicroTCA chassis. This is where they were doing direction finding and compliance testing of the signals that they intercepted, and in some cases jamming those signals, all across a very wideband bandwidth. So here are some links to some of the white papers and different application stories that are available on the website if folks are interested in further review. Some of these you do have to register for, but it's a very quick process. And from there, I'll turn it back to John.
Thank you, Justin. Excellent presentation. Before we get to our final speaker, just a reminder to the audience, keep the questions coming in. And now for our final speaker, Wayne McGee of Creative Electronic Systems, also known as CES. Wayne?
Thank you, John. I wanted to talk a little bit today about managing SWaP through extending the VPX concepts into a smaller scale using the VNX Vita 74 form factor. Reducing the size, weight, and power consumption of the rugged embedded computer systems while at the same time pushing the limits for I/O and computing performance has always been the holy grail of embedded design. The price pressure we're under and the need to shorten the time to market for newer technology calls for modularity and a maximum of reuse when designing a new system. The industry standards like VPX and VNX help to achieve this. VPX is just now hitting the mainstream of rugged embedded system designs and implementation, and by extending the same concepts that made VPX successful into a smaller form factor, VNX makes the modularity accessible in areas that were up to now dominated by custom designs. As you can see from the graphic here, a VNX module is about the size of a deck of playing cards. So what is VNX? VNX is a standard for plug-in modules that compute, do graphics processing for sensors, memory, and I/O. It was designed from the ground up to be inherently rugged and conduction cooled, and it was designed for SWaP critical applications. VNX is designed to be similarly architected to VPX systems but at a smaller size, lower power, and lower cost. It's not intended to replace VPX, but to extend the VPX architecture and the functionality into a smaller form factor marketplace. So the story behind VNX is that it's a standards-based small form factor ecosystem and infrastructure. The VITA 74 Technical Committee was established by the VITA Standards Organization in early 2010. The VITA 74 Committee has significant involvement from several merchant board vendors, system integrators, and defense primes. The standard status is released for trial use and is gaining wide acceptance. The VNX Marketing Committee was established by VSO in early 2014, and I happen to be the current chairperson of that committee. VNX used the existing standards to reduce technical risk and the schedule. VITA 46 VPX and VITA 65 Open VPX topology and pin assignments were adopted. VITA 57 FMC connector was chosen, and the PICMIG COM Express Mini SBC module was in mind when the sizes were developed. The VNX committee provided a reference chassis design in the specification. It utilizes both the 12.5 millimeter modules and the 19 millimeter modules and takes the form of a 4-slot cubicle chassis. This slide vividly illustrates the difference in the volumes that the different specifications that we're talking about today take up. You've got the 12.5 millimeter single module with a 200 pin connector on the left. You've got the 19 millimeter module with a 400 pin connector on the right. Now, if you take and normalize the volumes associated with these different form factors, and you normalize the 19 millimeter module to a 1.0, this gives you the relative volumes that the different implementations of these form factors take up. So as you can see, the 6U VPX is the largest, and then it scales down, and MicroTCA is right square in the middle, and then you'll see there on the low end you've got the VNX modules. So if you're like CES and you produce all of these two outside form factors, it gives you a very broad continuum of product to solve SWaP problems. Now, what VNX is not a system standard. The boxes don't have to look like a cube. The cards can go in any form factor enclosure, which is great for form, fit, function upgrades. As you can see here, they can also be used within other standards. VITA 75, which is another small form factor standard, you can put VITA 74 modules internal to a VITA 75 box. Half ATR, smart displays, and existing custom enclosures. All are easy to put one of these VNX modules in. So a little comparison here between VNX, VPX, and MicroTCA. On the connector, there are multiple suppliers for VNX and MicroTCA. There are not as many suppliers for VPX, and the VPX connectors are definitely more expensive. On the metalwork and hardware, the heat frame is relatively expensive to produce for VPX. You can use a heat spreader or a clamshell on VNX, and MicroTCA goes to a clamshell. With the wedge locks, VNX requires no wedge locks at all, and that is a big expense saver right there. When it comes to the thermal dissipation, obviously with the larger form factors, VPX is able to host the highest power processors. VNX goes for the low to medium power, and MicroTCA tends to fall into the medium power. We talked about the form factors, but the smallest of the form factors is the VTA-74 module. So how are VPX and VNX alike? They're both VITA standards. VNX benefited from the lessons that we learned introducing VPX. VNX was designed to allow the use of other standards, such as the COM Express Mini and the Mini PCI module. It was designed to be a scaled derivative of VPX. The backplane topology and connectivity is identical to a similarly equipped VPX system. VPX can support the higher power and higher performance processors, but VNX is coming of age with the latest system-on-chip processors. These processors are able to perform many useful tasks such as mission computing, display processing, sensor processing, I/O control, storage management, you name it. It allows you to put the right amount of processing power wherever on the vehicle you need to fit it, and sometimes in some pretty small places. So the VNX systems are definitely optimized for size, weight, and power, as well as cost. And both VNX and VPX have VITA marketing alliances, which are promoting the technology. Now this slide gives you an idea as to the scalability of the different modules. You've got the ability to do just strictly convection cooling. You can do strictly conduction cooling, or you can do forced air convection, and you can do it with a number of different techniques, whether blowing from the back or blowing from the bottom. We've also, in the ecosystem, developed commercial connector boxes as well as open frame development platforms that give you a lot of freedom when it comes to prototyping your system and getting the connectorization set. So a couple of VNX application examples. You've got a smart display there that can use single board computer, image processor, and storage modules as plug-ins to the smart display. For distributed architecture systems, such as the Victory architecture, you've got remote processing and I/O, a nav subsystem with GPS and SASM, as well as high-speed optical data buses, which are the bottom four connectors on the system that's in the lower right-hand corner of the slide. With the different processors that are available on these modules, you've got high-performance AMD G series, which is 4-core with dual GPUs, the R series SoC, the Intel Silvermont, the Power Architecture Core IQ, the NVIDIA K1, and ARM processors. All of these are able to be put into these systems. So it gives you quite a broad selection of different capability to choose the processor that you need. So with that, I'm going to turn it back over to John.
Thank you very much, Wayne. Excellent presentation. So why don't we get right to our Q&A? And since Wayne went last, well, Wayne will be the first question. So Wayne, how do you see the relationship between VPX and VNX in the future? Is it complementary or competitive? That's a question actually I thought of. Go ahead.
It is definitely complementary. As I mentioned, VNX is a derivative of VPX. It is able to extend the architecture just into a smaller form factor area, and we see it as a perfectly complementary architecture.
Okay. Keep those questions coming in, audience. Our next question for the audience is actually for Justin. For processing capability, is MicroTCA able to use Intel 4th generation Haswell processors or similar devices?
Yes, it is. There is a trick you could use in MicroTCA to use a second tongue, and actually it complies fully with the spec to use a second tongue to have more I/O and a larger pinout. And one thing that we have in design now is a Intel Xeon E5 version 3 processor, which is the fourth generation Haswell. And in there, you could also expand on the power that you bring into the board. So MicroTCA typically has 84 watts per slot limitation, but you could expand that. So you could use some of these higher performance, higher wattage processors with that trick, and we'll be introducing some boards later in the year that are Haswell single socket processors in MicroTCA.
Thanks, Justin. Our next question from the audience is for Mike. Mike, how important are embedded board standards for small form factor systems that serve as LRU or line replaceable units? I think is what they mean by LRU, compared to systems with line replaceable modules, LRMs.
All right, I'll take a stab at that one. My perspective is that if we build systems based on open architecture, we now involve an ecosystem of suppliers that from an I/O card standpoint allow us to have flexibility, modularity. So if a general purpose base mission computer provides, in the example that we just talked about, a fourth generation Haswell processor, and yet you have an avionics interface requirement for MIL Standards 1553 or AirLink 429 or maybe even a CAN bus interface for a vehicle, those types of add-on modules are readily available from trusted suppliers within the ecosystem that are building modules based on standards. So from a LRU standpoint, an LRU is replaceable as a box. However, the functionality is empowered through modularity. So we're able to leverage off-the-shelf available interoperable modules from the ecosystem around us. And that's in contrast to a line replaceable module approach, which is more along the lines of a VPX-based system, where the module itself can be replaced in the field. An LRU would be replaced, not a module within the system. So
it's an obsolescence path as well. As we're dealing with open standards, we got to deal with obsolescence, right? That's the always
that's another great point. Yep.
Okay. And now, I'm sorry to follow up on that question, but did you get a lot of that? Is that a lot of the feedback that you get from the end user is the obsolescence challenge as you apply more and more open standards? Are they more worried about that, or is that just a constant?
Well, I mean, Curtiss-Wright has an objective to provide a long life cycle for all of our products. So, we're constantly trying to provide systems for at least 7 years, and in many cases they're out there for more than a decade. And in those cases, you're right, there's an advantage to having something that can be upgraded with a like product and replaced for obsolescence. But yeah, I mean, the nature of military programs and the length of the programs dictate that we have to support a long life cycle. So open architecture avoids the dilemma of you're boxed in a corner now because it's proprietary and custom. And now you have a path towards migration that it's opened up now because of standards. Okay.
I have a question regarding for all of you guys later on, but I'm going to go back to the audience questions here. One for Justin. Does VETATEC provide FPGAs, processors, and systems in other open standard architectures?
Yes, we do. Actually, we do different types of FPGAs, processors, graphics boards, video mixers, and so on, and all different types of architectures. MicroTCA is just our architecture of choice because of the SWaP advantages, and it's such a versatile architecture. But actually advanced TCA is a big area in mil-aero where we're seeing a lot more interest and a big push with some of the programs out there that have chosen advanced TCA. So we'll be introducing some lots of specialty products in advanced TCA. Also, even VPX. If there's something special, specialty board or something different we could do in something like VPX where we're not recreating the wheel but doing something really different and innovative, we do also do specialty modules in those different architectures.
Okay. Just to follow up on that, when you're talking ATCA, maybe 6U VPX, obviously that's not small form factor. So do you think the increase in small form factors, is there still a strong, steady demand for the larger form factors? I mean, or is that cutting into that a little bit? Has everybody shrinking their systems, no matter which military trade show I go to? It's about reduced size in radios, GPS, et cetera.
Yeah, I think there's the overall trend to go smaller and smaller form factors. But in some cases, particularly when people use ATCA, it's really for that, just the amount that you could put in a blade, just a tremendous processing power. And there's only so many applications that require that, but there are more applications that are coming online that have chosen advanced TCA as the direction that they're going in, and many of them are sizable and attractive enough to really merit some attention.
Thanks, Justin. Next question is for Wayne. How has the released, quote, released for trial use, unquote, period gone? Are there any changes expected for the spec? And I'd like to add on to that person's question, Mike, can you give any timelines with those changes if you can, or rough guesses on timelines?
Sure. The specification so far is over halfway through the trial use period. We have found no problems in the spec that require changing the spec at all. We expect that by around October of next year, we expect the specification to be fully ratified. So I think that the technical committee did a great job. The fact that we're halfway through the period and we haven't found any problems with it. Again, reusing all of the lessons that were learned from VPX and the process that we went through there, I think that was a great way to eliminate that risk.
Thank you, Wayne. Wayne, I got another question here for you from the audience. How do you fasten the VNX modules to the chassis without the use of wedge locks?
The chassis that I showed in the slide, you take the top of the chassis off and the sides are loosened. You insert the module down onto the back plane from the top, and there's gap pad material that compresses. So you insert the modules into the back plane, you then ratchet down the sides, and then you put the top back on. And that's how those systems are. Now, we've got several applications of smart displays where depending on whether or not the particular application requires that they're removable, the display manufacturers developed a retainer that is able to hold the modules in, and then in the case where they don't want you removing the modules at all, they're fixed into place with brackets.
Okay, thank you, Wayne. Next question is for Mike. What type of qualification testing is being done to validate Curtiss-Wright's ultra-small, small form factor systems?
Well, we have developed a suite of mill standard and DO-160 tests that we're actually using across our entire product line. So the testing is not different for the miniature products. However, due to the low power nature of some of these products, the operating temperature range that we are testing to is even broader. So for example, the 8-port LRU Gigabit Ethernet switch that we talked about, that's a -40 to +85°C ambient operating temperature spec. And the testing that we do, includes the traditional mill standard 810 testing, mill standard 461 EMI testing, the power supply compliance standards 1275, 704, and the DO-160 standards for commercial aerospace as well. And the parameters that we select for vibration and shock tend to be at the extreme levels, and we test hybrid profiles that include both vehicle profiles as well as airborne profiles, so that we're subjecting these devices to the stresses of all the environments, so they are pre-validated for a variety of applications out of the gate.
Okay. Mike, speaking of your different form factors, Mike, I know you come from a Parvis background when Curtiss-Wright acquired Parvis. With all these new small form factors coming out there, where does that leave PC-104, which was the small form factor before we started talking about small form factors?
It is. It's been around a while, hasn't it?
Yeah.
PC-104 is one of those building blocks we showed in the slides. It is a tool in our bag of tricks. And so we have not abandoned PC-104 by any means. We view it as a tool, and particularly in our latest systems for any of the higher density I/O requirements for the PCIe 104 standard, we'll add on modules for FPGA or GPU or some advanced I/O that can't be satisfied through Mini PCI Express. So it's still alive and well. It so happens, as I shared with you, our latest generation systems use a COM Express mezzanine as opposed to a single board computer that's PC-104, and that's purely out of achieving our SWaP optimization goals and cost goals for the product. So it's not going away. It's, again, just a tool. It's one of those many options.
Okay. Thank you. And now for a question for Wayne. How does VNX look for the rugged industrial market? And how would a system for aerospace look versus a system for rugged industrials? Kind of the comparison, I think, is what they're looking for here.
One of the great things about the specification is that other than the connector on the modules, which was specified, the connectorization to the outside world was not specified. So just as we have one of the systems that's got completely commercial connectors on the transition module that allows you to use standard Radio Shack cables, you can configure the RTM on the system such that the connectorization meets the environment that it's going to be deployed in. So for the rugged systems, we use the big, expensive military connectors. For various degrees of industrialization, you could go with slightly less rugged connectors all the way to commercial connectors. And we have already had a number of inquiries from the oil and gas market on this product. So we believe that there are some applicable market adjacencies for rugged industrial applications.
Thank you, Wayne. Next question is for Justin. Do all rugged MicroTCA systems require wedge locks on the AMCs?
No, that's only for the most rugged level. There are various ruggedization levels in MicroTCA, and one of the examples we showed in the 1U, actually, we just used an extra screw to latch down the modules, which holds it securely in place, along with other ruggedization techniques throughout the chassis to meet the mill specs for ruggedization. But MicroTCA .3 is the most extreme level for hardened applications that require those very, very high levels for shock and vibration, and those are the ones that use the wedge locks. Otherwise, in the examples that we showed, those are using just our standard AMCs without.
Okay, thank you, Justin. Next question is for Mike. What types of military vehicle aircraft platforms are driving SWaP optimization the most? That's a good question. I'm curious, my first assumption would be unmanned payloads, unmanned system payloads, and obviously avionics upgrades because you only get so much room in the cockpit. Is that right, or is there other ones we're not?
Yeah, that would be the answer. That's right on.
Okay.
I think that the system integrators are trying to add more payload capabilities, and they're consolidating the mass of what's in there today when they're doing their upgrades to add more function, but it's still not add more weight. So I think you're right on. The unmanned vehicles, and now obviously there's different classes of unmanned vehicles from the high altitude, long endurance ones down to the micro ones, and all different sizes in between. And so there's a scale of what capabilities these are able to accomplish, and in some cases it's still quite a challenge from a physics standpoint to fit everything in such a small platform. But the unmanned vehicles are definitely at the forefront of pushing it. And obviously, when you look at tactical ground vehicles too, we talk about the Victory initiative, where the government wants to eliminate a lot of room that they could put butts in a seat for, and instead open it up and eliminate redundancy and excess weight so that the vehicles can have more capabilities but not have all the weight or the size.
I'd like to follow up on that question. We're doing a lot of content for our next June issue on the mega constellations and small satellites, and there's a lot of talk about how COTS and open standards are going to be used more and more in those areas. So do you see that as a growing area as well? Have you heard anything on that end on small sats or satellites and use of small form factors and standards in space? And then also for Wayne, anything on anybody looking at VNX for space apps at all?
As a matter of fact, we are engaged in talks, just as I'm sure you're aware that the space VPX specification has had a lot of publicity. We're engaged in talks right now about space VNX. Oh, it rolls off the tongue. I like it. And let us know when you guys are ready to talk about it. We'd love to cover it. But what about you, Mike? Anything on that? On you guys hear anything? Because you guys have some space platforms.
Yeah, we do. We're definitely seeing a trend towards using COTS products in space now. And we have some applications where we are now being deployed in that situation. But you referenced small satellites and things of that nature. We too are investigating that market. We have a group in Dublin, Ireland that has a lot of experience within the space application of taking COTS products, testing them for radiation hardening and suitability for up in space, and they have some good opportunities in front of them. So I'm optimistic.
Thank you. And Justin, anything you want to add on that? I kind of threw that out to the whole panel here.
Yeah, actually, MicroTCA is also being used in a satellite application. Actually, it's being used alongside next to VPX. So that's one thing that we like to say. If it's rugged enough for a space application, it's likely it's rugged enough for yours.
And so I got time for one or two more questions here. I got one for Wayne. What do you see for the long term as system of chip or SoC use becomes more prevalent for VNX and VPX markets?
Well, the great news is as we continue to get the processing power up without driving the watts up, that allows us to further increase the power that we're able to put into these systems. The current limitation on the single wide modules is around 15 watts, and the 19 millimeter modules is around 30 watts. And obviously, every time we get additional performance that we can put inside of those power envelopes, that helps us to provide a better equation for the system architects. And the same applies for 3U VPX as well, because what we all benefit from the increased power, and just having the ability to put the appropriate size package on the vehicle where it's needed will go a long way towards increasing the mission length and the ability of the machine to survive.
Excellent. Thank you, Wayne. And that brings us right up to our time limit today. Sorry we cannot get to all of your questions. Someone may get back to you after the ECAS with more information. I want to thank Mike Southworth, Justin Moll, and Wayne McGee for speaking today and for their excellent presentations. I'd also like to thank our sponsors, Creative Electronic Systems, also known as CES, Curtiss-Wright Defense Solutions, and VetaTech. This ECAS will be archived online today and will be available for 1 year. There will also be an MP3 version of the event available. Thank you all for attending, and I look forward to seeing you on future Military Embedded Systems and Open Systems Media ECAS. Goodbye.